Okay, now we have got the two modes which we just talked about. One is the user mode and one is the kernel mode. Okay, you can be a user. If you are a user, you're allowed to execute only those instructions which are in the user area. Okay, and there are some special instructions or privileged instructions in the user area also, which can't be executed by the user. So you need to be in a system mode or a in a system mode or in a kernel mode, which our batch monitor or resident monitor is. So resident monitor can execute into the protected memory areas as well as the privileged instructions. So if you're a user, you got to be in a, if there's an interrupt or fault, you have to be kernel mode. You can't do it off your own. And a kernel mode can switch onto the user mode as well. But as a batch monitor or resident monitor, you are in a system mode. You can execute the instructions. You can access the protected memory area as well as execute the privileged instructions. Okay. Now, if we talk about the first batch operating system in mid-1950s, it was by General Motors for use on IBM 701. Then it was refined and implemented on 704. And later on in 1960s, we had a lot of batch operating systems coming into play, and one of them is the IBSys. This is one of the first, you can say, the batch operating systems, improved ones for 7090 and 7094, mainframe computers of the IBM. Excuse me. Okay. Now, if you look at the IBM 7094 mainframe, this is from the Columbia University 1965. It looks like this mammoth big, computer. Okay, and your batch OS IBSys was installed on this giant computer. So the batch, actually did a kind of, increase in throughput, efficiency, and all. But still, in a batch, for example, you have a batch monitor here, and now you have the Oracle Resident Monitor, and we have some user program going on. It has some input-output, and then going on, then input-output, and then going on and so on. So when there is an input-output, what will happen is control goes back to the monitor, and monitor actually instructs CPU to whatever input-output is, do that, okay, and we are stuck. We are not actually doing any job. Okay, we are stuck with the input output, like the truck example I gave it, and we are stuck. So we want, now memories at the same time becomes cheap. So we say, why not do something else that we say, oh, if we have a structure like this, that we got a resident monitor here, then we're gonna use a program like job 1, I call it, and job 2 and job 3 and so on in the RAM memory, where because we have memory very cheap, we can extend it. Now the thing is that if here some program is doing and we have some kind of input output, then there's the next instruction to be done. Now when the input output comes, we know we can't do this program, okay, and we need to have some provision that the processor is not tied up with that input output, okay, rather something else, what's called as an interrupt driven or DMA, direct memory access. We have interrupt-driven direct memory access, where what will happen is direct memory access module deal that input-output, okay, and the rest of the things. No. We know we can't do the rest of the program. So what you can do is, because the J2 is actually the job second is in the memory, we can start executing the job. CPU starts executing the job 2's first instruction and so on. If input output comes here, we can go to the J3 and so on. And when this DMA finishes, this guy, you can come back again and start doing. So what will happen by that is you are not wasting a time of the CPU, right? Let me give you an example of a Mason building, which all the time I give to my students, that we have a brick wall. We're going to build a brick wall, and a guy Mason is building it. Now say for example, a truckload of bricks comes in, okay, whatever, and this is a truck, and a load of bricks is coming in. Now Mason itself goes to the truck and counts the bricks and pays the truck driver for those bricks, and then comes back. In the meantime, you're not building the wall. The main concern is building the wall. You're not doing that. So what you do is we say, man, what I do is I put up in a DMA in between, okay, and I tell this guy, the DMA, do these inputs, okay, and now DMA is controlled by the CPU, and because CPU is the boss. This is now CPU, for example. It asks DMA go and count the bricks and give the money to the truck driver and all that things. Now what will happen is it will start building the wall. It doesn't stop. But only thing is this DMA when finishes interrupts the CPU and tells CPU that, hey, I am done. So it keeps CPU does the bookkeeping. Okay, you are done with it and all that things. It should be knowing all the things. But the thing is that the CPU is not idle. CPU is not stuck with the input output. That is important. This is what DMA comes into play now. And we saw that we have a multiple jobs going on kind of a simultaneously. It's not simultaneously, but seeming simultaneously. So that's why we called it as multi-programmed batch operating system. Okay, so it is still a batch. We have still a batch, but it is now multi-programmed. We got different jobs going on together. Okay, if one job gets the I/O, the CPU can execute the next job. Now, if you don't have a multi-programming, say from the program A, it runs, it waits, then it will run, it will wait. So it's in unit programming, you have a lot of wastage. Okay. Now, if you have an A, B, and C, AB, for example, here, and or A, B, and C here runs here, and this is a combined thing. You have an A, B, and C going together, and if you look at this diagram here, for example, this is a process 1. You got the input output here. You can execute P2 in that time, and if both of these are not running, you can run P3. If all of three are not running, you can run P4. And when you are done here, you can come back to the P1 and P2 and so on. So there is no processor is nowhere idle, as you could see. Okay, but it needs a lot of hardware support as well. So it needs I/O routines supplied by the system. It needs actually the memory management, because the system must allocate the memory to several jobs. You not only have to allocate the jobs to several in a memory place, but you have to get also protection. Then you need to have CPU scheduling. The system must choose among several jobs ready to run. Okay, which are ready to run. Now there may be many processes ready to run. Okay, in this scenario, we are saying which one is running, but maybe at this moment P1 and at this moment P1, P2, P3, P4, all of the 4 can run. And now here at this moment there is an I/O, for example, of P1, and P2 is running. Now when P2 is running, you can't run the P3, but maybe P3 could have also been running. So which one to schedule? Okay, and allocation of devices and all those things will come into play. So if you are running, you have an I/O request, you are blocked, but when you are done with the I/O request, you are ready and you are waiting for scheduling. Okay, end of slice. This is time sharing. We'll talk about it later on. So now there is a lot more things to be done by the OS. Now this thing is technically called as multiprocessing. So if this is multitasking, sorry. Now this is technically called multitasking. So what is the difference between multitasking and multiprogramming? So we've got the multitasking operating system. Okay. Now multitasking operating system is someone, okay, which is implemented by maintaining the code and data. You have the code, you have the data, and you maintain that in not of one but several processes. Okay, you have several processes. You're maintaining their code and data in memory simultaneously. That you have a memory that, like I showed, we have a job 1, job 2, job 3. They all have their code and data, code and data, code and data, several processes together in the memory. Okay, and then you are multiplexing the processor and I/O devices among them. Now because you have a processor and now you have I/O devices, sometimes J1 is accessing processor, sometimes it is accessing I/O, the processor go to J2 and so on. Now you are scheduling these two between these jobs. This is the multitasking. So now what is the multiprogramming then? Okay. Now multiprogramming, if we go down a little bit, multiprogramming, we could say multiprogramming OS. Okay. What's multiprogramming OS? It is same which does the multitasking. That is the above one. Plus, it need to have sophisticated, memory protection. So it need to have memory protection. Okay, and also it needs to have concurrency control. If two processes are two jobs or processes are going simultaneously, they can have violations. What are these violations and what they can do in a concurrency control? We have a chapter on that. We'll talk that in later on. Okay. Now that can create a problem. Now if we have the jobs here and they're doing simultaneously and we don't have memory protection concurrency control, then it is a plain multitasking. But if we have the memory protection, say here job 1 is not, maybe user 1 which is executing job 1, it may not be mending with the J2 and J2 is not mending with the J3, or J1 is not writing anything into the J2 or reading from the J2 area. It has to read and write into its own area. So we have to give the memory protection that this process can run in this memory area only. Okay, and if there are two processes, if for example they are using the same variable, say some variable or some I/O device, say for example, I may say they're printing. This is also printing, this is also printing. Now there is an I/O device called printer. Now printer is a non-preemptive device. If you want to print some page, you can't print a line from this J1 process and another line from the J2 process. You have to first finish in its entirety the J1, then you can go to the J2. So if both of these guys are trying to access the printer, okay, so there comes the concurrency problem that if both of these guys are trying to access the printer, now we have to, if J1 is accessing printer, you got to lock it. You can't relinquish it, okay? You can't preempt it. You have to do the whole printing, and then and only then you can go for J2 to print. Now this kind of concurrency control is enforced in the multi-programming operating system and also the memory protections, which I said. But multitasking is a plain multitasking, and multi-programming is multitasking plus memory protection plus concurrency control. Okay, does it make sense? In multi, there's also one more operating system called multi-access operating system. Now in multi-access operating system, what we do is we have a main computer and then there are some terminals. You can access, it's a kind of operating system which allows simultaneous access to a computer system through two or more terminals. Okay. It may not imply the multi-programming, or it may imply the multi-programming. That's not a problem. But here what we are discussing is we have a different terminals and they're accessing a system. Like we have airline ticket reservation system, okay, where we can have thousands of terminals controlled by a single operating system. So that is a multi-access kind of operating system. Then there is a multiprocessor OS or multiprocessing OS. In this we have basically what? Multiple processors. These are multiple processors working together to do a job. For example, we've got a job 1, job 2 and job 3. Now they may individually may not be multi-programmed. Okay, maybe J1 is given to this processor 1, J2 is given to this guy, J3 is given to this guy. In totality they are doing multi-programming or multitasking, but as an individual processor they may be like what's called a uniprocessor or uniprogramming, that it's doing only one job, it's not interleaving. So or it may be. So in multiprocessor we have multiple processors working together. That's the examples of your multiprocessing OSs is the Linux, okay, and also the Windows, okay. Now we saw the multi-programming and we saw the multi-tasking. They do the things in the software, okay, but this guy multiprocessor do the same thing in the hardware. That's the difference, okay. Now multiprocessing systems can be either symmetric or it can be asymmetric, okay. Now if you see the diagram, okay, of the symmetric, this is a symmetric multiprocessor where we have many CPUs, okay, multiple processors. They actually are identical processors, and they're connected with a shared memory, common shared memory, okay. Like we have today multi-cores, we say core I, core i3, core i5, and so on. Now those multi-cores inside work as SMP, symmetric multiprocessor, multiprocess system. They treat those cores as separate processors, okay, and then they streamline the job. That is, we have the data or we have the tasks. They actually do internally what they share the workload, okay. So they move the tasks between the processors actually to balance the workload for efficiency. So if you have a job, you can break that into many, because we have threads as well, which we talk later on. You can have multi-threading programs going on. So one CPU is working on one thread, second is working on another thread, another is working on another thread, and they actually balance the workload efficiently. Okay, that's the symmetric multiprocessors. So this is one kind of multiprocessing system. Another kind is asymmetric. In asymmetric, if you look at this hardware system, okay, processors are commonly, dedicated to a specific task. For example, one processor may be dedicated to a disk operation, another to the video operation, and the rest of the standard processor tasks. So these systems do not have the flexibility to assign processors to the least loaded CPU. Say this is the least loaded CPU and this is the most loaded, so it can't balance the load like in SMP. Okay. So in SMP we had threads which were going on a multiple processors, but in asymmetric multiple processor, what will happen is applications run on one processor, but you can outsource small tasks to another processor, like in a client server type of architecture. So the master will be, for example, you are putting the load on this. The master, this is the master doing the main job, and some sort of little jobs will be outsourced to other processors. But there is no kind of load balancing as we see here, right? But they are specific to particular jobs. They are specific to some other kind of jobs, which we discuss later on in more detail. Okay, so this is what we have in the multi-processor or processing operating systems. Now, another kind of operating system is the real-time systems. Before real-time, we should talk about the time-sharing systems. Now, we've got a time-sharing systems. In this CPU is multiplexed among several jobs that are kept in memory, and on the disk, the CPU is allocated a job only if the job is in a memory. Yeah, like this. If you have a job in a memory, you can do that. But if it is on some I/O, you can go to the swap to the disk and get back. First, you get from the disk the jobs and make a queue of ready queues. And if you have completed this, okay. But if it is not, you can swap it to the disk and get it back then later on. Okay, and CPU can execute multiplex your resources which are on the ready queue. Now here in case of your multiprogramming, this is Timesharing is again a multi-programming a kind of operating system, but here we work on the response time. So we need a quick response time rather than in multi-programming we are trying to reduce the idle time of the CPU, but here we are interested mostly in the response time. All the jobs should be happy. Okay, all the jobs should get some kind of time quickly. So that's why we sometimes do these jobs in a round robin fashion. We give some time slice. We give some time slice to each job. So this job one is executing. It has some time slice. Maybe it finishes or maybe it doesn't. But we will preempt CPU from it. Give to the next. If it finishes in this time slice, okay. If not, we give to the next. We give to the next. And then this guy, which is not finished, it goes on a back, or if it is an input-output or something, it goes to the disk, or it comes back later on when it is ready. But if it is ready, we still snatch or preempt CPU from that process and get it on the back of the queue. Okay, so that everybody gets a good response time. Nobody is actually unhappy. Okay. So we've got clearly some advantages of this time-sharing operating system. It provides the advantage of quick response. That's the most important thing we're talking about. For example, transaction processing systems, we need a quick response there. Avoids duplication of software. It reduces CPU idle time, but problem of reliability, question of security and integrity of user programs and data, and problem of data communication, and there are many more things which we need to take care of when it's a time sharing. And we'll discuss these systems later on in detail, and we take them there. Now we have the next is a real-time systems. Okay. Now in terms of real-time systems, we here need a, we have a stimulus and we need a response. Okay. So here we have a real-world activities. If we have a real-world activities, okay, we try to implement those here, which this operating system tracks the real-world activities. We need to finish our job in a time-based manner. Okay, if the external events occur, we need to respond very quickly, right? In a real-time systems, a primary objective of is to provide quick event response. So we have a stimulus and we respond it, okay, and so that we meet the scheduling deadlines. Here, the user convenience or resource utilization, they are of secondary concern, which were primary concern other OSs. Here, the user convenience is they are of secondary concern. If we have thousands of interrupts, we should not miss even a single event, okay, and we should finish our job without fail. For example, military, we say like here we have a radar system. Say for example, radar system, and here is a missile. It may be a nuclear missile which can come into your way, and your radar system is watching the external stimuluses, and now you have a battery which can fire your Scud missiles to destroy these missiles in the air. Now you don't have to worry about user conveniences and coloring and graphics and all those things where the processor wastes its time in a look and feel, but we need a quick response to the stimulus. If the missile is coming, this missile is to be destroyed in air, so we have to quickly access the situation and fire these missiles to destroy it in an air. Okay, or in an ICU, we are in an ICU and the patient is on a bed, okay, and we are monitoring its heartbeat, its pressure, blood pressure, and a lot more things. If something goes down, we have to say for a switch on the maybe ventilator or maybe something else. So if we don't have to miss any event, okay, and we have to finish the job within a time schedule and without fail. Okay. Now, how hard you are in your doing things? The real-time operating systems are of two types. One is the hard, real-time system, and another is the soft real-time system. Okay. Now here in the soft real-time system does what it does the best effort to meet the response requirements of a real-time application, but can't guarantee, okay, um, uh, that it can't guarantee that it will meet all the conditions, like digital audio or multimedia system, okay, fallen collected like digital telephone, that is also in this category, okay. But in a hard real-time systems, they are typically dedicated to processing real-time applications. They're fully dedicated. They, you know, they are meant to meet the response requirements of application under all conditions. They will guarantee that they're gonna do it. Like we got a missile system. That missile can be a nuclear missile that can make your country a wasteland. So you can't miss it. Okay, and you need a hard real-time systems to cater those needs. Okay, but if you can have a softness, you can have a soft real-time system. So these are the some features of real-time OSs. The concurrency within an application. You can programmer can indicate some part of the application should be executed concurrently. Okay, and the OS consider execution of each such part as a process, a separate process. Okay, and we have process priorities. We can give priorities to one process, and then we schedule them according to their priorities. And the priorities are based on deadline area schedulings. Okay, where the deadline is closer, the priority increases, and we try to finish that at early as possible. Now there are some domains, special situations with external systems as events, and your system actually then associates interrupts with them and specify event handling actions for them. Okay, and the policies and overheads of OS should be predictable. It should be predictable, and reliability is the most important thing in case of the real-time OSs, because they are highly reliable. We know we're gonna do it with whatever occur. No, it will survive whatever situation it is. It has to do, and that too before deadline. Okay. No. So now the next one is the network OS. So in order to transmit signals across a network, it's necessary for computers to communicate this modem. We have got network interface card and ICs. So an OS, network operating system, provides with these protocols necessary to achieve this goal. In fact, this is now with all default any operating system you have, they have all these features now on inbuilt. Okay. So network operating systems not only allow communication across the network, they also allow the network administrator to organize resources, control access, ensure the network is operating efficiently. Sharing of network resources can be peer-to-peer, where everyone is of same, like we have BitTorrent, we download from the peers. Nobody is master, nobody is slave, but there could be a server client based architecture also, where one is the boss and other are the subordinates. Okay, in a peer-to-peer, everybody is of the same rank, so nobody is a boss and nobody is a slave. We can do any such things, okay, in the network operating system. Now the examples of network operating systems are like Windows 2003, Microsoft Windows Server, Unix, Linux, Mac OS, novel NetWares, BSDs. There are a lot more and newer ones. So advantage we have is a centralized servers. We can have centralized server in the client-server architecture. We have a highly secure. We can have a security in the server. Server manages all the security about the clients and all those things. Okay. If you want to upgrade to new technology, the hardware can be easily integrated into the system. Remote access to server is possible from different locations. Okay. Now there are disadvantages as well. High cost of buying and running a server. Dependency on a central location for most operations. Regular maintenance and updates are required. Okay, these things are there, but there is a lot of cost benefits as well when we have a client-server based architecture, and we have, for example, a system. We have powerful server, and we have a clients which does not have so powerful, and they want say sometimes the processing power. They can ask for the server. Okay, they need the RAM, the hard drive, the storages. You can share with each other. You can share the resources. You can share the files. So it is really a great thing to do in today's world, especially. Now, one of the operating system called a distributed operating system is a kind of same thing. Let me make this as a box. Okay, this is the same box which has these networks, but on overall we have an abstraction layer. Okay, which is of distributed operating system, which makes us as a user distributed OSs over it, and it makes us think as if it is a one whole big system. Okay, in a network operating system, you log on to a particular system explicitly. You know, I'm logging on to a particular system, and you know this is on that system, and if you want to access this system, you have to log on to that system explicitly using login and password, username and password. But here, you never know which processor you are using, where in whose hard disk you have your files, and all those things. You don't know in distributed OS. So it's a kind of abstraction. So you are abstracted from all these internal details. Otherwise, internally it's a network. So it is the distributed operating system is nothing but a network operating system. Over it, we have a layer of distributing OS, right? Now we have many more other than these. Like we got the desktop OSs, we got the mobile OSs. Okay, like we call them as a handheld systems, and a lot more, like we've got Androids and Mac OSs, and there are a lot more operating systems which can be there, and there are some clustered systems also, so which you take up in later on. And for now, I think it's enough, and for an introduction, you will come up all these things later on. Okay, until then, ma salama.